Okay, just 1 second. I don't know how to turn it on. Okay, so this is the PCD for Codechef Starters 187. In this PCD, we will discuss 5 problems from the Div2 contest. The 5 problems that we will discuss are incremental game, the first problem, then or what, that is the second problem, distinct representations, anti-Savarism, and then major infection. This was supposed to be the fifth problem, I guess, but it got only one submission, so it is at the sixth position right now um, in the Div2 contest. Okay, so the first problem here, incremental game. This problem says that Alice and Bob found 2 piles of stones, one with X stones, another one with Y stones. They decide to play a game using these piles, and both of these are trying to one up each other. Basically, they will try to defeat each other, and they will play the game while taking turns. Alice will go first. On Alice's first turn, she can choose one of the piles and remove at least one and at most K stones from the pile. After that, each player will choose one of the 2 piles and strictly remove more and has to remove strictly more stones from it than their opponent's previous move removed. And in case if they are not able to do this, then they will lose. Okay, so let me explain the problem here. So the happen is
Your
Alice
voice is not
will
audible.
go. Am I audible? Hello, am I audible?
Yeah.
Okay, nice. I think I got disconnected due to the internet issue. Let me change my Wi-Fi
Yeah.
once so that it doesn't happen again.
Yeah, like while presenting also, like we were not able to hear your voice only.
Okay, okay, no problem. I will just start explaining from the scratch once again.
Okay.
Okay, so I hope you are able to see my screen. It's visible, right?
Yeah, it's visible.
Okay, great. Yeah, so let me read the problem. The problem said Alice and Bob found 2 piles of stones, one with X stones, another one with Y stones. They are playing a game using these piles. So they both will go one by one in turns. First move is of Alice. She can choose one pile and remove at least one and at most n stones from the pile. After that, both of them will go one by one. Bob, then Alice, then Bob, then Alice, and so on. And they have to remove strictly more stones uh, from the pile they choose than the number of stones that the opponent had removed in the last turn. I think it would be more clear here. So Alice and Bob are 2 people. They are playing a game. There are 2 piles of stones. One is having X number of stones, another one is having Y number of stones. Right. Let's say Y is greater than X for now. Okay. So what will happen is Alice will go first. She has to choose a pile choose a pile and then remove maybe p number of stones, where this p should lie in the range from 1 to k. Yeah, it's up to Alice how many she wants to remove, but it should be in the range from 1 to k. After that, it would be Bob's turn, then Alice's turn again, then Bob's turn, then Alice's turn, and so on. You know, only Alice's first move is different. After that, for every move, these two will have the choice. First of all, choose one of the piles. Then, let's say in the last move, Alice had removed 10 number of stones. So now Bob has to remove at least 11 number of stones. So P must be greater than the number of stones the previous guy or the other guy had removed in the previous move. So if it's Bob's turn and in the last move Alice had removed 10 stones, so in that case Bob will have to remove at least 11 stones. I hope the problem is clear. Can you guys please confirm it in chat if it is clear or not? Just write yes or no in the chat. Okay, great. Yeah, so the problem was easy to understand. The um and actually like the first problem is just cakewalk. Now all we have to do is we just have to tell like we are being given x, y, and k. If both of these players play optimally, then who will win? Either the answer will be Alice or Bob. We will have to tell which one of these is true. So all you had to do was just think about some different cases. Like let's just take a simple example. An example test case: x is 4, k is 4. Sorry, x is 4, y is 4, and k is 10. Right. Right after reading the problem, you will definitely go to the sample test cases if you don't know about the solution. If you know about the solution, like if you have already got some idea right after reading the problem, then you will think about it. Otherwise, you read the sample test case. So here we are having two piles, each having 4 stones, and k is 10. So the output is supposed to be Alice. And the way she wins is she takes 4 stones from the first pile. It is allowed since 4 is less than equal to k. And after that, Bob will have to choose a pile with at least 5 stones because he has to remove at least 5 stones. But the two piles that are there are having stones 0 and 4. So Bob does not have any pile that he can remove. So Bob will lose. I hope it makes sense. Yes or no? Like in this case, there were two piles, each having 4 stones. So what Alice can do is she can just choose a complete pile. Now, when she chooses a complete pile, she's basically taking out 4 stones. Now, after Alice's turn, the first pile would be empty. The second pile will have 4 stones, but Bob has to remove at least 5 stones because he has to remove more stones than the number of stones that Alice had removed. So Bob would not be able to choose this pile. Like he can choose this pile, but he won't have 5 stones to remove. So Bob will lose. Right. So from this sample test case, you should have got the idea that if let's say the there are two the very like the least you should have been able to think after doing the sample test case is that in case if x is equal to y and k is greater than equal to x, in that case you can just remove one of these piles completely and Bob would not be able to win, right? K should be greater than x so that you are able to remove the complete pile. And if you remove a complete pile and the other pile is also having the same size, Bob would not be able to win. When you think a little more about this, you should get to the you should get the idea for any x comma y, as long as x is less than equal to k and y is less than equal to k, if you just remove the larger pile, If you just remove the larger pile completely, Bob will have, let's say, x is 5 and y is 7, and you just remove the complete pile which was having 7 stones. In that case, Bob will have to remove at least 8 stones, but he will not have a pile with 8 number of stones, right? I hope it makes sense. So as long as x is less than equal to k and y is less than equal to k, it doesn't really matter whether x is greater or y is greater or both of them are equal, because you will just remove the larger pile and Bob will have to remove one more stone than the larger pile that you had removed. And obviously, that does not exist. So Alice will win in this case. Right. This was the actual thought process in which I had approached this problem, like how I got, how I had got the idea for this problem. Nextly, since I thought about this approach, by the way, there is one more suggestion. Like even before coming up to the sample test case, there is one more thing I had thought about. That is, this k is making the problem more difficult. What if k tended to infinity? In that case, the first move and all the other moves that Alice and Bob will play are going to be exactly the same, right? In the first move, Alice has to remove at least one stone and at most k number of stones. If k is infinite, then Alice can remove any number of stones of his choice, sorry, of her choice, right? So it will make it easier for us to think on how like Alice can decide what is the best move for her, right? So in any way you got it, it is very doable till this point. Nextly, since we have thought about the case where k is greater than both x and y, we should think about the case where k is smaller than both of x and y also. Like if what if this happens? So let's discuss this also. One pile is having x stones, another pile is having y stones. Now, no matter which pile Alice chooses and tries to remove, since k is smaller than both x and y, at the end of the day, like if Alice chooses this pile, it will have some less number of stones. It will have x minus k number of stones, but it doesn't matter. Bob can just remove this complete pile. You know, like for Bob, he will have 2 piles left. One of them will have x minus k stones, another one will have y stones. Now, whichever one of these two is larger, Bob can just remove that larger pile, and the same thing that like we were doing to make sure that Bob can't play a move, that will happen with us. If Bob takes down the larger pile, then we will not have any legal move left and we will lose. Right. So no matter which pile you choose, if k is smaller than both x and y, then Bob will win for sure. Right. I hope it's very clear till this point. Now let's talk about the third possible case. What if k is smaller than one of x and y and greater than another one? So let's consider the case where k is like in this range. Let's say y is having more stones than x. Or you can just imagine x having more stones than y. It doesn't really matter. It will not change the answer. We are just taking a general case. So in this kind of a case, you have a smaller pile and you have a larger pile, right? Now, if you just remove all of these stones, Bob can definitely remove more stones than you. In fact, he can just take down the larger pile completely and you will lose for sure, right? If you choose the smaller pile now, you will definitely lose because Bob will just take down this complete pile. So, one thing is clear, we should definitely remove stones from this pile. Now, if you remove less number of stones, Bob can take up the all the remaining stones to make things worse for you, right? So another intuition that we should have is you should try to remove as many stones as possible, or basically we can say you should try to remove k number of stones completely. And you know that k is less than y, so you will remove as many stones as you can. So what will happen after this is Bob will have two choices left. One of them is having a pile with X number of stones. Another one is the second pile with Y minus K number of stones. Right. You know one thing for sure. For Bob or even for Alice, the best thing to do is always just remove as many stones as you can from the larger pile. Right. If you can remove the larger pile completely, you will win. Like whoever is making the move. If he removes the larger pile, he will win. And in case of Bob, he does not have any constraint of how many stones he can choose. So obviously, he will just pick up the larger of these two, whichever pile is having more number of stones. Right. I hope it makes sense. Let me just recap this thing once in case if anybody has any confusion. We saw if k is greater than both x and y, then Alice was able to win by completely removing the larger pile. If x is if k is smaller than both x and y, in that case, no matter which move Alice takes, Bob would be able to make a move and Bob will just take down the larger pile. So Alice will lose for sure. Right. You know one thing for sure. If Alice can take down the larger pile, he will win. But if he fails to take the larger pile and Bob gets a move and he can take out the larger pile, then Alice will lose. Right. So for these two cases, answer was pretty straightforward. Now for the case when k is greater than one of the integers and smaller than one of the integers, let's consider this exact case where k is greater than equal to x and smaller than y, because we have covered all the other cases. Then here, if you take the smaller pile, Bob will just take down the larger pile completely and you will not have any move to make. So you will lose for sure here. So the better move for you, or the only possible good move for you, is to take out stones from the larger pile. And you would like to remove as many stones as you can. So let's say you have removed k stones from this pile, larger pile, and now it's Bob's turn. Since you have taken k stones in the last move, it means that Bob cannot choose this pile with x stones because k was already greater than or equal to x. So now, no matter what Bob wants, he cannot choose this pile, right? And the only choice he has is to remove this pile if y minus k is greater than or equal, or sorry, if this thing is greater than equal, if this thing is greater than k, strictly greater than k, only then Bob can choose this pile. If y minus k is less than or equal to k, in that case, Bob will not be able to make any move and Bob will lose. And in case if y minus k is greater than k, then Bob can just remove this pile completely and Bob will win because Alice will not be able to make any move in future. So in a nutshell, like what we have got so far is, for this specific case where k is in between x and y, if k is if k is smaller than or equal to, or I should say k is greater than y minus k, like if this k is greater than y minus k or even equal to y minus k, in those scenarios, Bob will lose here. Like Bob will lose, so Alice will win. Otherwise, Bob will win. So, like if k is smaller than y minus k, basically k is the number of stones you removed, and y minus k is the number of stones Bob intends to remove in the next turn. So if y minus k is greater than k, then Bob will just remove this complete pile and he will win because he would have removed the larger pile. And if k is greater than equal to y minus k, then the remaining number of stones would not be enough for Bob to make a move. So Alice will win in this case. Right. Basically, what you want to do is make the first move such that Bob never gets a chance to make a move. If you can do this, then Alice will win. Otherwise, Bob will win. So here is a recap for everything that we have done here, like the case work that we have done here. If k is greater than or equal to x and k is greater than or equal to y, then Alice is able to win by removing the larger pile. If k is less than x and k is less than y, then Alice is just losing straightforward because no matter what he does, Bob will be able to play a move and he will take the larger pile down. Then, if, like for the case when k is in the range from smaller guy, like if k is greater than equal to the smaller guy and smaller than the bigger guy, then it depends upon the case whether k is greater than equal to y minus k or k is smaller than y minus k. If k is greater than equal to y minus k, then Alice is winning. Otherwise, Bob is winning. That's it. Okay. So, guys, are you good to go with this? Like, are you able to understand the idea, main idea? And by the way, especially for Codechef's editorials, like at least for today's editorial, since all the problems are ad hoc, it's my recommendation that please don't try to understand like for the whole casework that I tell you. I might tell you for the perspective that if you're not able to solve the problem, you should have a resource to check out. Like you should have a solution with which you can match your answer. But what you should do is watch the editorial a little bit, and as soon as you find out a point, let's say I marked this thing and this is, let's say, something that you had not noticed in the contest yourself, then just pause the video and try to solve the rest of the problem yourself. If you look at the whole casework that I have done, then you won't really learn anything by yourself. Like you will learn only a little bit, not that much. It will just defeat the point of practicing if you um, look out for a step by step explanation. Okay, so now let's look at the code part here. So the code is pretty simple. For every test case, here I have been taking the inputs of x, y, and k. After that, in case if x is greater than y, then I just swapped it because this is related to my implementation. I did want to write a shorter code, so that's why I did swap it. Um, doesn't matter what is the value of x and what is the value of y. Like if x is 10 and y is 7, or you say x is 7 and y is 10, whatever answer you were having for this particular test case, you will still have the same answer for this particular test case. So swapping won't change the answer. It just made my implementation a little simpler, um, cleaner. So if k is greater than the bigger guy, then answer is Alice. If k is smaller than the smaller guy, then the answer is Bob. If like if you are coming till this line, then it means k is greater than equal to the smaller guy and smaller than the middle guy, then sorry, smaller than the bigger guy, huh? And then in that case, if k is greater than equal to y minus k, then the answer is Alice, otherwise Bob. So that's how my code looks like. Let's move on to the second problem. So yep, let's have a minute. Let's have a 1 minute break, and then we will discuss the second problem. Okay, so there is one doubt asked by someone. Let me clear that once and then we will move on to the next problem. So somebody is asking regarding the equal condition. So see, for the condition where I said y is greater than equal to k, sorry, I said k is greater than equal to y, where y is the larger guy. Right now we are assuming that y is greater than equal to x. Then in that case, Alice is moving. I hope, um, like, okay, you are trying to ask now that when k is greater than y, then Alice will win. And I think you're confused regarding the part of when k is equal to y. Then how are we deciding which one will win? Is this your doubt, Mohsen? Sorry, Mohan. Mohan. Was there someone like Mohsen also? No, not here. Yeah. So see, um, k equal to y means you can remove at most y number of stones, and you know that y is the number of stones in the bigger pile. So don't you agree that this thing also means that you can remove the bigger pile completely? And if you can remove the bigger pile completely, then you are winning, of course. We have discussed this thing over and over. um, if you, let's say, have two piles and you remove the bigger pile completely, then the next guy, Bob, will have to remove five stones, but he has only three stones left, right? So Bob will lose for sure. And this thing will work even if x is equal to y. Even in that case, Bob will not be able to win. So is it clear now?
Can you take through that notes? I will ask one question. You go through notes. I have one question. Like
Okay.
you showed on it. In this, like you showed, there is a like here there is a three in left side, and one more example was four. Suppose you consider five. So five is greater than four. So you will take first one four. I mean like that one like you can you take with example and explain once more this part only.
Okay. Okay. So if you have four stones here and five stones here, then you
Okay.
can just remove all of these five stones. Now Bob will have to remove six number of stones, and he can't remove six stones from here.
Okay. But what is the K you took here?
We are talking about k being greater than or equal to the bigger guy.
Okay.
Basically, you're not having any
Oh,
constraint here. If k is greater than or equal to the bigger guy, then it means you can remove as many stones as you want.
okay, okay, got it. Thanks, thanks.
Okay, great. So now let's talk about the second problem. The second problem, named as forward, says that we are being given um, up two positive integers. We are being given two positive integers n and x. We have to find any permutation p of the integers from 1 to n such that the number of indices I satisfying pi bitwise or with I is equal to x. This, like, the number of indices should be as large as possible. Okay, so that's the problem. If multiple permutations satisfy the answer, you can return any one of them. So if, let's say, you have something like n equal to 6, x equal to 5, then it means you have to find out a permutation of these six integers 1, 2, 3, 4, 5, 6, such that, like, you have to find out some permutation of them such that after permutation, if you name them as p1, p2, p3, p4, p5, and p6, and their indices are 1, 2, 3, 4, 5, 6, then the number of indices for which pi bitwise or I, this thing is equal to x. Like, this thing should hold for as many integers, like as many possible values of I as possible. So one possible way here is, let's look at the sample test case straight. Okay, we have a sample test case n6, right? Okay, let's just look at the answer directly. 563142. So this is the solution given to us in the sample test cases. The indices are 1, 2, 3, 4, 5, 6. So what happens here is the bitwise OR of these two people is 5. Bitwise OR of these two is 6. Bitwise OR here is 3. Bitwise OR here is 5. Bitwise OR here is also 5. And bitwise OR here is 6. So we are basically having three positions where you are having the bitwise OR equal for both of the elements. Like for these three pairs, like the bitwise OR of these people, and these people is equal to X. And what we have to do is we just have to find out any permutation P for which we are having as many such indices as possible. Now, right after reading the value of n index, you might not be able to figure out what should be the total number of indices in the answer. Like you can't do this thing manually. So are you guys at least able to understand the problem? Like what we have to do here? Please tell me in chat, yes or no. Okay, Mohan got it. What about uh, Akarsh? Sorry. Yeah, Akarsh. Okay, great. So for this problem, I will tell you about the way in which I approach this. Um, like during the contest, you don't really prove everything. You go with a lot of gut feeling and um, with the intuitions about which thing is making sense. So I will tell you about the solution for this problem in that way. If you go with an approach which is proving the solution correct, then you will just waste a lot of time and will uh, apparently get your rating drop down. So let me just tell you about the way in which I approached the problem. The first thing I did is I knew one thing. Since I can't manually um, think much about which element should come at which place and all, uh, a good way for approaching such problems is just look at the sample test cases first. So in the sample test cases, I liked these two sample tests. For the other two, they did not really look very promising because in one of them, n is 3, so you will never have the fourth bit set. So if x is equal to 4, like you are just not having any index for which pi bitwise or I is x. And for the second case, there is only one bit. So I took the example of n equal to 6 and x equal to 5 because it looked like a good example to me. Not too complicated, not too simple. Since this is a bitwise problem, always think about such problems in terms of binary representation or basically bitwise representation, representing numbers in terms of bits. So x should be written as 101 and the numbers from 1 to 6 that you have would be written like 001, 010, 011, 100, 101 and 110. Right. These are the 6 numbers you have. So one thing that I noticed right away as soon as I wrote this much is for any number like 3 or basically any number which is having this middle bit set which is not set in x, um like if this bit is set and you do its bitwise or with any number, then at the end of the day, whatever number you form, the bits that are set here will still remain set. Now this bit will still remain set even in the end number you form. Like let me take an example. Yeah. So let me take an example. If you do 3 bitwise or with any number, like no matter what number you choose here, the like the last two bits or the least two significant bits that are already set in 3 will remain set. Like even if the number here is 0, you will still have these two bits set. So you know one thing, if like you place this guy on the ith index, then no matter what the value of I is, pi or I can never be equal to x. Right. This was my idea. And this thing is not just valid for pi equal to 3, but even for I equal to 3. For the index 3, whatever element you place there, pi or basically p3 mod, p3 bitwise or with 3 will never be equal to x. So one thing that I decided straight away right at this point was, in the final array, for all I which are having at least one bit set in the number which is not set in the number x, basically any bit which is not set in x but is set in the number, for all those I will just set pi equal to I itself. Like in this case, we are having three numbers, that is 2, 3, and 6. These are the three numbers that are having the second least significant bit set, which is not set in x. So we will just keep in the final answer array. In the final answer array, you will have 2, 3, and 6 being placed at their positions only. This is one thing you should definitely do. You will not have any disadvantage here. You will only have advantages. Nextly, the idea that I got was, I was just trying to combine the remaining people, the people who are basically proper submasks. Yeah, this is a term used for such numbers. If for a number, let's say 1001, all the bits that are set in this number are set in some other number also, like let's say 11 101101 or anything. The two bits that are set here are set here also. So this number is called a set submask of this number. Or another way of defining the word submask is, for any number, all the numbers in which there is no extra bit set, all of them would be considered submask of this number. Right. So right now we are only considering the numbers that are submasks of x. These people, I wanted to combine them in some way so that I do maximize the number of pi or I equal to x thing. So here I got one idea. There is one bit that is, there is one number 001 and there is another number 100. If I just place these two people at each other's positions, then like if I place 100 here and if I place 001 here, the indices for these numbers are 001 and 100. So the bitwise ORs of these numbers will just become 101, that is equal to 5. Right, if I do something like this. So what I got in mind was, for any I which is a submask of x, basically if I is a submask of x, then in that case what I can do is set pi equal to i's or x and pi's or x equal to I. Set it in this way. Basically, i's or x will tell me about all the bits that are set in x but not in I. If I is a number like, if let's say x is a number like 101101 and I is a number like 100101, then in that case, the bitwise XOR of both of these will give me the bits that are set in X but not in Y. That are set in X but not in I. And with the help of this, I can find out a perfect pair. Like these two are actually perfect pairs for each other. They are like made for each other people. Na? Right. These people are like made for each other. So this is good for us. Just combine people like these with each other and you are good to go. Another thing that we do know here is this i's or x and this I. Both of these numbers will be submasks of X. So both of these would be smaller than X also. Right. We do know about this thing as well. So like I just pointed this thing out because some people might have a concern later on, which I will point out. So I just pointed this thing out for once. Please confirm till this point whether everything is clear or not. How do we know the strategy will always work? Um, that's actually a good question. And during the contest, I did not really spend on any time at thinking about whether the strategy will always work or not. Here is actually a tip for you. Whenever you are giving a contest on CodeChef, since CodeChef does not have any penalties for wrong answers, so as soon as you think about an approach which seems to be working and you cannot find out any counter case for this, always just try submitting it on it once on CodeChef, unless the implementation is too complicated. If the implementation is small, like for this problem, the implementation is very small, so just code it and try to submit it once. Like this is not a very good way for the interview preparation or for competitive programming in general, but it's more like we are exploiting the feature of CodeChef that we don't have any penalties. By the way, let me tell you a little bit about the kind of things that came up in my mind before I submitted the solution. So I tried to think about it in a way like for the case when X is okay, let me think about a different way. Okay, I think I have a different way. This is similar to the editorial that has been given by CodeChef. So for I, which is a submask of X, you want to set a PI such that like this PI should have all the bits that are not set in I but are set in X. And basically this PI should be equal to X XOR I or maybe something else. It can be anything else, but it should definitely have all the bits that are set in X XOR I for sure. And you see, X and I does not have any common bits. So this PI thing for any integer I that is a submask, this PI thing is nothing but X minus I, right? This is X minus I basically. Now, your PI cannot be smaller than X minus I because you have to keep all of these bits set that are set in X minus I. Although you can add some extra bits, like if I is 2 and X is, let's say, 10, I is 2, that is represented as 1 0 in um, binary representation, and X is 10, that is represented as 1 0 1 0 in binary representation. Then you need to have PI equal to X minus I, that is equal to 8. Hai you need to have at least, you need to have, oh, wait, it's 000, yeah? Yeah. So you need to have at least this bit set in PI, but you might consider having some more extra bits set in PI, like you can have PI equal to 10 also, which is having both of these bits set. You will still have I bitwise or with PI equal to 10, but the problem here is you are just wasting a bit. Maybe you could have used 10 at some other place. Like in this example, you can't use it, but you might be able to find out some cases where you actually make things worse for you in some way. So if you, let's say, had something like X equal to 111 maybe, or 11101 maybe, and I was equal to 11100, and if you end up choosing PI equal to 11001, they are still having their bitwise or equal to X here. But the problem is you just wasted this number. You could have just picked up this guy also. So during the contest, I did not really prove anything, and I don't have any proof even till right now, any mathematical proof that will prove everything for sure that we will always have the best answer. But we can at least have an intuition that choosing a PI, larger PI, might make things worse for you, because this PI is like this 11001 number is more useful for you in comparison to this guy, right? I hope you are able to at least feel this. Um, and I think that even the official editorial does not have any mathematical concrete proof. I did skim through the official editorial to see if there was any mathematical proof, and I could not see it. It was also something related to this only, that um, like you must have PI being at least this much, and if you add any extra bits while making sure that PI is still a submask of X, then you will only make things worse. PI will only become larger, which might make things worse, might not make things worse, but it will not have any benefit for sure. Okay, one more thing. Sometimes this might happen that I is less than equal to n, and I is a submask of X, but X minus I, or basically I's or X, this thing is greater than n. This thing might happen a few times because X can be greater than n, X can be as large as 2 into n. So this might cause trouble for you. Actually, X can be as large as 2 into n. So this might cause trouble for you at some places. If you don't write this check, 1 in 4, that part, can you repeat? 1 in 4. Okay, so what I discussed about 1 in 4 was, like in this particular case, you wanted Pi or I to be equal to X. So one idea that came up in my mind was, initially I have put up Pi equal to I for everyone, and now for the ones where I is a submask of X, I can just make swaps in a way such that like this 001 is missing this first bit now. So swap it with a number which is having the first bit set, that is 100. Similarly, for this 100, you have this last bit missing. So this 001 is a perfect match for 100. Basically, both of these are perfect match for each other. Like Bhagwan ne bana di jod for these people. So you can just come make pairs like these. For the one which is X, um, for the guy X, it does not really need any partner, and everyone else was already getting its partner. Like the more I tried to think about it, I could not think of a case where I would need this X guy, like the guy where Pi and X are equal to X, um, to be swapped with someone else to make things good or bad. I just found that everyone else will form some pairs with each other, um, other than X. Like in case if X is less than equal to n, then other than X, everyone will form a pair, and X will not really need to be swapped with anyone to uh, make sure Pi or I becomes equal to X for someone. Nextly, in case if X is greater than n, then obviously you don't need to worry about what will happen with Px. You can just skip it, right? So Mohan, is it fine? And I'm sorry in case if I again said your name as Mohsen earlier. Actually, I have a friend with name Mohsen, so that's why. Um,
It's okay, fine. It's okay, fine. No, I was having doubt. Like, see, for that one and four, you thought there should be a number in first bit one, so that you can swap. You thought, but how you got to know? Like in code, how you'll get to know that there's a one more number with bit four. Like, starting bit is one. How you'll
we
get to know in
do it with
code?
eyes or X now.
That's what I was asking.
We will do it by eyes or X. Basically,
Yeah.
okay, got it.
Uh,
Oh, great. Then let's move on to the code part. So I'm taking the inputs here for every test case. Then I initialize my answer with answer I equal to I for everyone initially. And then I am iterating from left to right. Um, for the cases where answer I is not equal to I, it means that it has already been swapped. So I'm skipping it. For the cases where I or X is not equal to X, it means I is not a submask of X. So just continue. Otherwise, I will find out the perfect partner for the index I and will make a swap with it. And at the end, I will print my answer. So this is how I implemented it. You don't necessarily have to implement it in the same way. You don't even have to understand my implementation. Just implement it in any way you like. The like this is something you should be able to do by yourself. You don't need to rely on anyone else for coding this much. If you are not able to code it yourself, if you are struggling, then it means you need more practice. So even in that case, you don't really need to go to someone else code and understand it step by step. Just put more efforts by yourself. So I don't think we have anything else to discuss for the code. Shall we move on to the next problem? Okay, great. Now we will discuss the third problem, that is distinct representations. This problem says that we are being given a binary string S, that is a string consisting of only zeros and ones. We have to modify it by performing the following operation. In the operation, we just choose an index I such that Si is equal to Si plus 2, Si plus 1 is equal to Si plus 3, and Si is not equal to Si plus 1. Then we swap Si plus 1 and Si plus 2. Or in more simple words, we can choose any substring that is equal to 0101 and make it 0011, or we can choose a substring that is equal to 1010 and make it equal to 1100. Basically, we are swapping the middle two characters, and we have to count the number of distinct binary strings that we can make by performing this operation several, even zero number of times, possibly zero number of times. Since the answer might be too huge, print it modulo this. So that's it for the problem. Yeah, so this is the C problem. We are being given a binary string S, which is having 0101011110, whatever. Basically, it is a binary string. And we are being allowed to apply a type of operation in which we choose some integer I, basically some index I, such that Si is equal to Si plus 2, Si plus 1 equal to Si plus 3, and Si should not be equal to S of I plus 1. These are the three conditions that should hold on. And these conditions will hold on in cases in the only substrings for which it will hold true is either 0101. Basically, these two are equal, and these two are different, or 1010. Right. So what we do in the operation is, after choosing this much, we swap Si plus 1 and Si plus 2. So the string like 0101 will become 0011, and the string will become 1100. So the first and the last characters of these substrings are equal, like they are still the same as they were earlier, but the middle characters have been swapped. From 0101 it becomes 0010, and from 1010, it became 1100. We have to tell what is the total number of distinct strings that we can form. So that is what we have to tell. Like we have to tell the distinct strings that we can form by applying this operation any number of times. So let me take one example to add more clarity here. Let's say the string is 101010. Okay, by the way, I will tell you about my thought process for this problem also. Like for the constructive problems, there is no particular way of solving a problem. It's more like you see something in the problem, you get some intuitions, you get some idea, and you think in that direction. You don't get just one idea, you get multiple ideas. And then you um, decide which idea you want to think more and so on until you get to the solution. So I will tell you about my thought process on how I did solve the problem. And obviously, there is no particular way for this kind of a problem on how you should approach them. So um, one thing I did is right after reading the problem, I looked at the sample test because this is a constructive problem which is easier to deal with after looking at the sample test cases, or basically after thinking about random uh, possible test cases and try to find out some pattern for solving the problem. So what I observed here was we had a string 010101, and I tried to think about it myself. What are the possible strings that I can obtain? So one thing I can do is I can choose this substring and apply an operation on this, or I can choose this substring. Sorry, I'm having cold. Yeah, so either I can choose this substring, or I can choose this substring, or I can choose this substring. I can apply operation on any of these. Right. This was my initial thought. Then I tried to check what if I apply operation on one. Can I say that I will never be able to apply any other operation in that case? So basically, one possible string that I can obtain is 010101. Basically, we don't apply any operation. Another possibility is you apply operation on the blue part. So it becomes 0011 and the remaining string is the 01. Or the other case is you apply on the red part, that is 0 and then 1100 and then 1. And then the fourth case, that is the green part, 010011. These are the four strings that we can obtain. I hope the colorful pens are making it a little easier for you to see like how the operations are being applied. This is actually an advantage of iPad. Yep, this is one thing that I wanted to talk about by a long time. Since I started using iPad during contests, I feel that my speed has improved because during the contest, if I am using, like if I was doing it on a copy pen and had to use only one pen, then it would have been a lot more messy. Whereas with iPad, you can draw different colors and it would be easier for you to not get lost. Though the difference is not very big, it is generally on the easier problems only, where you have to do some random case working or basically some dry runs. Um, but yeah, I think it's worth mentioning. Okay, so this was the sample test case. Now, what I got in my mind was when I apply an operation, these people, like you will get um, two people adjacent which are equal to each other. And you see, if you want to apply an operation, you should have something like 0101 or 1010. So one thing is clear. Like you cannot have two of these people being involved in an operation or these two people involved in an operation together. है ना? So the only people who can get involved in an operation is like if you had maybe like a zero here, if you had something like 1010 here. Basically, if you had a string like 010101 and 0, you could choose this first part and make it 00111, and then you will again have one possible substring where you can apply an operation. So your string now will become 0011100. Right. So basically the thing that I noticed here is if I apply an operation on this substring, then um, this part and this part that I could see earlier are non-operatable. And like earlier you were having three possible substrings here, which on which you could apply the operation. But if you apply operation on one of these, then the neighboring people will not be will not have any possibility anymore. Basically, if you had a string, maybe you are having 01010101, maybe 0 here, 1 here, and 0 here, anything like this. And you picked up four characters here to apply an operation. Then earlier, like it might, depending upon the string, maybe you could apply an operation on this substring, maybe you could apply an operation on this substring, maybe you could apply, you could still apply here. Basically, these two substrings where you could apply an operation would no longer be valid. Similarly, um, this substring and this substring would also be invalid now. So after the operation, it will become 0011. So now for the substrings that were like having more than one character of these four will no longer be able to have any operations. So the idea I got was either I can apply an operation on this substring or maybe even on, like I can apply operation on either this substring or maybe on this substring. Or if I apply an operation on this substring, then I cannot apply operation on this and this. Right. You are getting some case here. You know? So it's basically becoming like if you choose some I for applying an operation, let's say this was your I, this was your I minus 1, and this was your I minus 2, and this was your I minus 3. Let's say this is I plus 1, I plus 2, and I plus 3. Then if you chose some I, then you cannot choose I minus 1 or I minus 2 or I plus 1 or I plus 2. Those options would not be there for you. And now, if you choose some index I, then for any j, like you can still apply an operation on any j, index j, such that j is less than equal to I minus 3 or j is greater than equal to I plus 3. I believe this might be looking a little complicated or a little complex, but this is how the problems are. Anna, you are not solving something very trivial, because if you were solving something very trivial, then probably would not have come to the PCD, right? You are coming up to the PCD because you could not solve a problem. So it's okay if it is looking complex. Like I'm just mentioning this because I see a lot of people um, nowadays complain in everyone's PCD that the explanation looked complicated to them. So it is meant to be look complicated. You know, if you are thinking that someone will create an explanation that would be very easy to understand, it would give you a step-by-step explanation for what to do at every step, then in that case, you would never have a long-term improvement. And I see like this is something I've seen in a lot of people. The ones who actually tended to just have spoon-feeded solutions never go past specialist. Expert is the max that they reach. Like you will never see a candidate master with this kind of an attitude to expect a spoon feeded solution. So like I just mentioned it in general, I'm not really trying to target anyone. I'm not targeting anyone in general. Uh, like in specific, it's very general thing. Skip it if you don't like it. Okay, anyways, let's discuss the rest about it. So what we have got so far is we have realized that the problem is more like we have to find out the number of ways of choosing um, some subset of indices such that if you choose an index I, then the condition on Si being equal to Si plus 2, Si plus 1 being equal to Si plus 3, and Si not being different from Si plus 1. Like these three conditions should definitely hold for I if you are choosing an integer index I. And moreover, you let's say you have chosen indices I1, I2, I3, I4 in the sorted order. Then the absolute difference between any two consecutive ones, let's say I1 and I2, should be at least 3. Hai I can, like, this is how I modified the problem. The original problem was to just find out the number of distinct substrings that I can, distinct strings that I can create. From there on, I tried to see one thing, that where can I apply operations, and I figured out that if I apply an operation here, I cannot apply operation for the next index or the next index. But for the next index, basically for index I can still apply operation on I plus 3, even if I'm applying an operation on I. Both of these can coexist at the same time, but operation on I and I plus 1 cannot coexist. This was one idea that I had got. Nextly, there is one more thing that I had realized. Like I did not prove it because I had a very strong gut feeling regarding this. If I like, let's say if I chose 4 indices I equal to 1, 4, 10, and let's say 14 as the indices where I would be applying where I will apply operations. And on the other hand, if I chose some other indices, any subset other than this of indices, then the strings that would be generated by the two subsets would be different. So if I had chosen, let's say 1, 4, and 10 only, or if I had chosen 1, 4, 9, and 14 or 13 or whatever, in those cases, the resultant strings at the end of the day would be different. And actually, it's not difficult to prove because the thing is, if I choose I equal to 1, then Si, basically Si plus 1, that is S2, and S3 would be swapped, right? And if I chose like I equal to 1, 4, 10, and 14, then it means that S2, S3, S5, S6, S11, S12, and S4, 15, S16. These would be swapped together, right? So if you pick up any distinct combination of the indices you choose, you will have different operations being applied here, like the different characters being swapped together. So at the end of the day, the final substring, like the final string you will have is going to be distinct for distinct operations you applied. Like this is one way in which you can prove it. And to be honest, during the contest, I did not even try to prove it this much. Like I did not spend even a single minute at proving it because of how sure I was that something like this would happen. Okay, nextly, I did try to just formulate it a little bit. That hey, if I choose some index I, then I cannot choose I plus 1 or I plus 2. So this problem is now basically a very standard DP problem. It's it's a simple variation of a very standard DP problem in which you have to find out number of subsequences of an array or something such that if you choose like every consecutive elements that will come in the subsequence should be at least k indices apart from each other. Basically, the elements that you're choosing for every pair of those elements, they should be at least k indices apart from each other. है ना? In this current problem, this k is actually equal to 3 only. It is fixed. We don't have a variable k. And there is just one extra condition, like for the subsequences that we can choose. Here the condition is that si, like the substring from si to si plus 3, basically like the exact same condition that we had seen earlier. Si should be equal to si plus 2, si plus 1 should be equal to si plus 3, and si should not be equal to si plus 2. Sorry, si plus 1. These three conditions should be satisfied for I, only then it can be picked up. So it became like this kind of a problem. Now, if you have never solved a problem like this one before, then I would recommend you to leave this current problem for now and go to Chrome and try to search for this kind of a problem, where I think this would be present in Striver's A to Z sheet also. Striver A to Z sheet, maybe I will pick it up. And if I go to dynamic programming there, like I'm not doing any paid promotion on anything for Striver. It's just because in my case, I did refer to Striver's DP sheet at the very beginning of my journey. That's why I am opening it, because I know that like he has shown it pretty well. So I think there must be a problem here, which is like this, or maybe no. Okay, I can't see it. I'm not sure if it has or not. Then CSCS must have it in general. Okay, it would be difficult to see if CSCS has it or not. I don't know, like if I get the problem link, I will share it in the description. If I don't find it, then it's okay. Told you about the normal problem in general. Like the normal problem is that you would be given an array. You have to find out number of subsequences or some information regarding the subsequences, where there is a condition that for the subsequences, every two consecutive elements must be at least k indices apart. This is a very, very standard problem. You must solve it because like just like in today's contest, as you got this problem, um, like you got a very simple modification of this problem. It happens quite frequently, especially for platforms like AdCoder, where they generally give variations of the standard problems. And even for Codechef, it is not that rare. And even for Code Forces, um, Div 3 and Div 4 contests, it is quite likely to come in some contests. And it would be very important for you for other means also. Like if you're solving this problem, your understanding for dynamic programming will improve a lot. So I will show you my implementation, but it might not make a lot of sense for you, because like you can just compare it now. I have solved dynamic programming at a lot of platforms like AdCoder DP, CACS problem set, and Striver A to Z sheet, and then a lot of problems on Code Forces and Codechef and random contests also, even on Lead Code. So obviously the way in which I do implement might not be very beginner friendly for you. Um, but the way in which I implement it is something you should try to learn. Like you should try to um, understand it at least by yourself, because it's actually a very good way of implementing. So the first thing that I did here is I took the inputs, then I created a DP array, and Okay, so what is my DP state telling me here? So here my DP I is telling me the number of um, distinct distinct strings that I can form with first I characters. है ना? So if you have a string, this I is actually denoting that DPI will tell you the number of distinct strings that you can have from the first I characters in this given string. So the base case here is simply DPI equal to, DP0 equal to 1. For the zero length prefix, or basically while having zero characters, there is exactly one possible distinct string, that is an empty string. The answer we will have is going to be DPN. Like this is going to be our output. We have discussed the state. We have discussed the base case. This is going to be our output because we have to consider all the characters at the end of the day. As for the transitions, so like if you know the answer for the first I characters, here you have two choices for the next character. Either you apply an operation on the ith index or you don't. If you apply an operation here, like if you are eligible to apply an operation and you do apply an operation, then you know that you like for these next three characters as well, you would have got like uh, it should be something like DP of I plus 3, like you will reach this state. Now you have already considered I characters, now you have considered these three characters as well. For the fourth character you will still have a choice whether you want to apply an operation or not. So you would actually reach this state DP of I plus 3, right? Like if you had the first I characters here, then you had 0 1 0 1. Currently we had choice for this character whether we want to apply an operation here or not, right? So if you apply an operation on this guy, then you know that these two will get swapped out. So there is no point of going to DP of I plus 1 or DP of I plus 2, because you know that these are actually swapped. If you want to go to DP of I plus 1 or DP of I plus 2, then you will have to have some other states. But what we can do is just simply jump to the next state. That there is one possible way to reach, like we have got one extra different substring or one different string. We can form one different string here. So like for this guy, we will still have a choice whether we want to apply an operation on this guy or not. As we just saw that if you choose some index I, then you cannot apply on I plus 1 or I plus 2, but you still can apply on I plus 3. That's why we will move on to DP of I plus 3. So my transition looked like this. In the case if I can apply an operation and DP of I plus 1 would be incremented by DP of I, no matter whether I can apply an operation or not, because I had two choices whether I will apply an operation here or not. Basically, whether I will take the current guy in the subsequence or not. So even if I don't take the current guy in the subsequence, like for the I will just move on to the next guy in that case. I like this would be very easy for you to understand if you have already solved this problem. Whatever I gave you some hints about here, I have not explained it completely like an editorial, like not editorial, but like a normal class. Because right now we are actually in a post contest discussion, not a class. And I am expecting that you already do this thing first. After that, watch this in case if you need it. Otherwise, don't even watch it. So if you have done this problem, like this implementation is very easy for you. So I had two choices, not pick or pick. For the not pick case, the transition will look like this. For the pick wala case, I could have written the condition here, like all this condition at this point also, but I just thought of creating another lambda function here. and then use it to check if I can apply an operation here or not, and if I can apply the operation, write the condition here, and at the end, this is my answer. So, in a nutshell, the recommendation from my side is solve the problem that I told you about first. If you are not able to solve that problem, then you don't need to upsolve this problem. There is no point of solve like there is no point of trying to solve a more difficult problem if you can't solve an easier problem. है ना? This was the bigger problem, and I did divide it into easier problems for you. If you can't solve this problem yourself, then it means that you need more practice before coming up to the original problem. And in my opinion, it's better to just focus on this part, which you can do yourself, instead of looking out for step-by-step explanation for this thing. And by the way, guys, please give me some feedback about this also. Like, what do you think about it? Um, like I think that in this video I have gone a little more blunt, uh, like directly telling you that this is just useless to expect a step-by-step explanation. Um, so please tell me about it. I'm still sure about it that a step-by-step explanation would be a waste of time for you mainly, because you won't really learn much there. Like you will have a feeling that you are improving, but you won't improve in general, because you are not doing stuff by yourself in that case. Anyways, we can move on to the next problem now. In case if you have any doubts, then please ask in the chat. And I was never close to using DP for this problem. Okay, like that happens. Even in my case, when I was new to competitive programming, I also generally used to have no idea about the DP problems. Or even if I had ideas about DP problems, I used to generally fail at applying the DP. Like even after knowing that this can be solved using DP, I still used to fail. Um, and that thing changed when I did learn about this new way of implementation, like the push DP thing, the way of writing code like this. Once I got to know about this possible way, my journey for DP just changed drastically. Okay, so charging set. Yeah, giving intuitions about the problem is fine. Okay, great. So shall we move on to the next problem? I think we can. So guys, you have a minute. Try to read this, understand this, and then I will discuss this. Okay, so this is the fourth problem of div 2 contest, anti-Savarism. This problem says that we are this is bullshit. Like yeah, so first of all, they defined what they consider as an empty subarray. In simple words, any subsequence that is not a subarray, that would be an empty subarray. This is a simple way of calling it, and they have given a formal definition, a mathematical one. You can read it yourself also. And we are being given an array A which is having at least 4 elements, and a Boolean array B of length n and an integer k, we are required to perform the following operation. Sorry, we can apply the following operation in which we choose an integer I such that bi is equal to 1, and then we increase ai by 1. We have to find the minimum number of operations required to obtain an anti-subarray whose sum is at least x. It is guaranteed that bi contains at least one element equal to 1. So basically, the problem is saying we are being given an array A and a Boolean array B. Boolean array will have either true or false, or you can say 0, 1, 0, 1, whatever you say. I think they call it as 0, 1, 0, 1. So we are being told that we can apply an operation like if bi is 1 for some I, then we can increment the value of ai by 1. This will cost you one operation. This will cost you one operation. Okay. What we want to do is we want to make sure that this array A should have at least one anti-subarray with sum greater than equal to x. This integer x would also be given to us in the problem statement. I hope the problem is clear. We are being given two arrays A and B. A is an integer array, B is a Boolean array. We want to make sure that A has at least one anti-subarray which is having sum greater than equal to x. And for making sure this happens, we are allowed to make operations. In one operation, you will choose an integer index I such that bi is 1, and you will increment ai by 1. This is something that we can do. Nextly, we want to do this thing in minimum number of operations, and I think we have to tell the minimum number of operations required only. What is the minimum number of operations required? Now, what is this anti-subarray? If you read the problem, it would be pretty clear that if you are having a subsequence such that it is not a subarray, if you are having a subsequence that is not a subarray, then that would be called as an empty subsequence. And do remember one thing, it must have at least two elements, because if you have only one element, then that would be a subarray as well in itself. And so if you have an array like 4, 1, 2, 5, 6, 1, and you choose these three people, then yeah, this is a subsequence, but this is an array subarray as well. So this would not be considered as an anti-subarray. Or if you just choose this one guy, then yeah, this is again a subsequence, but it is an array in itself as well. And obviously you cannot choose an empty subsequence, because if you are considering an empty subsequence, then that is also an empty subarray. So you have to choose something like this such that there should be at least one element in the middle that is not there in the chosen elements. So you will have a subarray, like you will have an empty subarray if there is at least one element missing in the middle of the chosen elements. Let's pick up an example here, because these are the ad hoc problems which are easier to solve after looking at the sample test cases and trying to figure out some patterns from there. This is how I do solve problems. And to be honest, like I did perform really well in this contest. I can't really declare my rank here, but it was like, you can think about it as one of the best in the country for today's contest on Codechef. Like we know that CodeChef does not have all the best coders giving contests, so it's not a achievement. But I just wanted to give you some confidence that hey, if somebody got this kind of a rank and he's suggesting that this is a good approach for solving the problem, then that's actually going to be a good approach. So we have elements minus 200, 500, and 2. And the Boolean array is 1, 1, 1, 1, 1, 1 for everyone. So now I think it's like the thing that will come up in your mind initially, the thing that came up in my mind initially was I just wanted to choose this guy and x, what is the value of x here? Okay, x is 9. X is 9 here. So I just wanted to choose this guy and wanted to do when like I just wanted that the answer should be 0 because I got one guy and it is already greater than equal to 9. So I don't need to apply any operations. But then I remembered that hey, I cannot have um, an an NT subarray with just one element. I need to have at least two elements. So if I keep these two elements, then that would be troublesome for me because I will have to apply like 109 operations here. And if I do something like keep these two, or yep, if I keep these two, then that would also be bad. So the only good option I have is just choose these two people. Choose these two people. They are currently having a sum of 7, but I want the sum of 9. So I can just say that I need this many like this many number of operations in order to make the sum equal to x. Right. That is one thing that I can do. So for now, like for simplifying the problem, I just assume that hey, let's say bi is 1 for all I. I just assumed this thing to make the problem simple for me to start with. And once I get some approach for this simplified case, then I will try to think about the original problem. Right. So the idea that came up in my mind for solving this problem was for having an empty subarray, what you need is among all the elements that you have chosen, there must be a hole in the middle. Basically, there must be an element between these people, which is having some elements picked up from the left of it and some elements being picked up from the right of it. And the current guy should not be picked up. So basically, there should be some element that is not chosen, but there are some people from the left that have been chosen, and there are some people on the right that have been chosen. And I just want to make sure that the sum of these and these should be equal to something greater than equal to x. Right. So obviously, since I can choose subsequences, if I fix some value for this guy that would be skipped, I would just like to pick up all of the positive integers on the left hand side and all of the positive integers on the right hand side to maximize my sum of the anti subarray. Right. This is this is a very intuitive thing, I believe, that you want to maximize the sum of anti subarrays. So what if I say for every guy, one by one, just consider it as the whole of an anti subarray. Find the sum of all of the elements on the left hand side and the sum of all of the elements on the right hand side, all the positive elements, and you would get some sum. This thing should be greater than or equal to x. If this is less than x, then the answer would be x minus sum. Right. This is the approach I got in mind. I had thought about a few edge cases also. Like there should be at least one element on the left and at least one element on the right. So this I should be in the range from this only, right? This should be in this range from 1 to n minus 2, or basically you can say greater than 0 and less than n minus 1. Nextly, what if there is no positive element on the right hand side? then you will have to pick up some negative element. You would, like, if you have, let's say, -1, -10, and -4 on the right hand side, there is no positive element. But you need to pick up at least one element from the right hand side also, to make sure that this is the whole of an empty subarray, right? So you would just like to pick up the largest possible value on the right hand side. Similarly for the left hand side, if there is no positive value, then just choose the largest possible value. That is basically the least negative while taking the sums, right? So this was the main idea. Obviously, it can be like, I think this can be optimized even further. Maybe you can do something like find out the first occurrence of a positive element from right side, from the left side, and now for all of these elements here, the total sum of the positive elements on LHS and RHS is pretty much constant. That is total sum minus AI and all. Like, you can try to think about some optimizations if you can find any, but I don't think it is worth much. So I did not try to optimize it any further. And this was my idea. Guys, does it make sense? If anyone is there in the meet right now, please tell me. Okay, great. So now let's talk about the more difficult thing. Right now, the problem is pretty simple. When we have assumed that BI would be one for everyone, right? But there is no guarantee. In fact, the problem would not have been given to us if BI was always one. You know? The problem is at this like, it is a diff 2D problem because BI might be equal to anything, right? So you might have a situation where you found an empty subarray, you found an empty subarray such that the sum of the people that you picked up on the left hand side and the sum of the people that you picked up on the right hand side is, let's say, 27 and x was equal to 30. So you might have an idea that, hey, the answer is nothing but 3. You need to apply only 3 operations. But there is a possibility that for all the people that you picked up, the value of L is just 0. What if this happens? Like, what if this happens that, the value of B is just 0 for all of these people? Then in that case, what you would have to do is you would have to pick up one guy which might be even having a negative value from either the right hand side or the left hand side, such that BI is 1 for that guy. Right? Do you guys agree with this? In case if BI is 0 for all the people that you have picked up, then you might need to find out, like, you might need to pick up a guy for which BI is 1, even if the value of that element is negative, so that you are at least able to apply the operations to make the answer, to get to the answer. So basically, let's say the sum of the left elements is sum left, sum L. The sum of the right elements is sum R, right? And we are only considering the sum of the positive elements, by the way. We are taking all the positive elements from the left and the right. Nextly, if this thing is already greater than or equal to x, then the problem is already done for you. If it is less than x, then you might have a situation if sum of L is like sum of L plus sum of R. You do something like this, you find out the number of operations you need, and that would be your answer. Only and only if there is at least one positive element on the left hand side or at least one positive element on the right hand side which is having the BI equal to 1. Otherwise in this whole array, other than this guy that you are about to remove, you must find out the largest element for which BI is equal to 1. And then what we will do is we will just say that your current sum of all the elements that you have picked up is sum L plus sum R minus this value of the element for which bi was equal to 1. Let's say if it was y. So this is the sum of the elements that you have picked up on which you want to apply the operation. Now, yep, this is the number of elements that you are picking up in your NT subarray, and you want to make the sum equal to x. So this is the number of operations you need to apply. Right. Our answer should look something like this. I hope it makes sense. And actually, this is the solution I saw from the editorial. In my case, my idea was the exact same till this point. But after this point, instead of noticing this part that I can just find out the biggest point, biggest person with bi equal to 1 in the array other than this guy, I did not notice this thing. Instead, I just thought that maybe I can just simply apply dp on the left and the right. Like I can just apply dp here such that, let's say, pre of I1 tells me sum of non-empty prefix or sum of any non-empty subsequence of prefix of length I, or maybe I will write it at the other place. So like the thing that I thought about, here I have explained the solution from the editorial. You will have a few more edge cases, like you need to make sure that you have picked up at least one element from the left hand side, at least one element from the right hand side. In case if all the elements on the left hand side were negative, then you will have to pick up the largest of those negative elements. Similar logic is applied for the right hand side as well. And in my case, I generally prefer to write a DP solution if I feel there's a chance of having some edge cases in greedy solution. And like if I have some confidence for the for the DP solution, then I just straight away go for the DP solution. So right now in the PCD, I will explain more about the DP solution. I have explained enough for the greedy solution. And for the rest of the solution, if you want step-by-step cases, you can look at the official editorial. Otherwise, I think this much is doable for that. Nextly, for the for my approach, what I did is for some particular value of I, as I have decided that hey, I have to pick up some elements from here, some elements from here. So I just decided I will create some DP states. One DP state will tell me about this. One will tell me about this. So what will happen is I should know about the largest sum that I can get such that there is nobody on the left hand side which has got bi equal to 1, but there is one guy which has got bi equal to 1 on the right hand side, or there is one guy on the left hand side that has bi equal to 1 but nobody on the right hand side, or both of the sides are having bi equal to 1. Hai, or maybe both of the sides are having bi equal to 0. In this case, this thing must be greater than equal to x, otherwise this is pointless. So I had this kind of an idea. I will explain more. I just wanted to give you the intuition, like the intuition that I got. I had an intuition like this one only, that use like create some DP state for every prefix to find out the maximum sum of any subsequence in this prefix. Basically, pre of I should tell me about the max sum of any non-empty subsequence from the prefix of length I. ठीक है? Nextly, there is a problem. How will I know about whether the elements from the left hand side had any bi equal to 1 or not? What about the right hand side and all? So that is why I created the state in a little different way. Along with this one dimension for I kept one more dimension, 0 comma 0 or 1. It would be 1 in case if I have found anyone which is having like which is having bi equal to 1, and in case if I don't find anyone with bi equal to 1 on the left hand side, then this thing would be 0. So I just created this kind of states. Now for every I, all I have to do is, for every possible value of I say there are two possible things. One of them is increasable sum. Sorry, increasable sum. Basically, the sum, the largest sum of any um, non or anti subarray. Yeah, the largest sum of any anti subarray which does not have this index I, such that there is at least one guy in the non-empty, in the non-empty, sorry, in the anti subarray, such that bi is equal to 1 for it. So there are three possible cases. Either you pick up the guy which is having bi equal to 1 on the right hand side, or on the left hand side, or on both sides. So increasable sum would be equal to the maximum of pre I minus 1 0 um, plus suffix of I plus 1 with 1, or prefix I minus 1 with 1 plus suff I plus 1 0, or pre I minus 1 1 plus suff I plus 1 1. I got the value of increasable sum to be something like this. Nextly, I created another variable that is non-increasable sum. Sorry, non-increasable sum. In this case, it would either be any of these cases, or this case. Basically, there is this case also now where you pick up some elements from the left and some elements from the right. None of them have bi equal to 1, but the sum of all of these is already greater than equal to x. So this non-increasable sum will have the maximum of all of these four. And I will just have a condition that if this thing is greater than equal to x, then my answer is already 0. Otherwise, my answer will be x minus increasable sum. Increasable. So is it making sense? By the way, in case if anybody who is watching the video is getting confused, just a reminder that you don't really need to follow the way in which I solved the problem. You can stick with this implementation, this solution also. This was the intended solution for the problem. My solution is just a little more complicated for, it's going to be more complicated for most of the people. The only reason I went up with this method is because before this thing could strike up in my mind, I got the idea for DP, and I was pretty confident with applying dynamic programming. That's why I did go with DP and created my states in this way, and that's it. So, Srujit, is it good enough? Like, do you have any doubts, or shall we move on? Okay, that's great. If it's clear, that's great. Let's see the code. So in my code, what I've okay, it's I think I have some stuff to remove first. Yeah, so I took the inputs first, then I created a function with name getDP because I wanted to create two DP states, one for the prefixes, one for the suffixes. So instead of writing the same logic twice, I created a function which will return me for the prefixes. And then what I will do is after getting for the prefixes, I will just reverse the array and then get for the suffixes, and then I will again reverse the arrays. So this is how you can avoid writing the same logic again and again. And for the part of DP transitions, I think it's better if you try to understand it after reading it yourself. Like the base case is for the first guy, depending upon the value of B0, I will update DP of 00 or DP of 01 with the value of A0. Then for every member from 1 to n, um, if I pick up a guy, then whatever the BI value of that guy is, if I'm picking up a guy, um, this would be updated, like the value of the current guy plus the previous max that I could get so far. That is for the last guy, whether have got any bi equal to 0, bi equal to 1 so far or not, regarding that thing. Nextly, TPI1 is about the case where you want to make sure, like you want to keep track of the maximum sum you can obtain if um, you are having at least one guy with bi equal to 1 right now. So that will look like this. In case of not pick, you don't really do any changes. You just update the values simply. Once you have created the prefix and suffix arrays like this, after that, you will go for all I from 0 to n minus, sorry, from all I equal to 1 to n minus 2. I created two variables, int increasable sum, that is the sum that I can increase by applying operations, and non-increasable sum, that is the sum that I cannot increase by applying operations. If the non-increasable sum is already greater than or equal to x, then in that case, I can just break. I don't really need to do anything. Answer is 0, that's it. Otherwise, I will update the value of answer, and at the end, I will print the answer. Okay, so let's move on to the next problem. Maybe we can have a 1 minute break, and then I will discuss this problem. At it this problem that we will discuss now was actually solved by very less people. Like out of all of the participants, only 27 people managed to solve this in today's contest. And uh, Okay, you can tell me what you thought, and in the meanwhile, I will explain it. So, for the ones who are watching the recording, would also not feel like uh, they got any disruptions. Okay, so the problem name is major infection. In this problem, we are being given an array. We can apply the following operation as many times as we want, where we have to choose a non-empty contiguous subarray, that is an array from index L to index R, let's say, um, that has a majority element. Then we will set all of the elements of the subarray equal to M, where M is the majority element. 1 minute. Yeah, I'm back. Okay, so in this problem, we have been given an array A of size n. We are being told that we can apply a type of operation in which we choose a subarray, and that subarray should have a majority element. Then we will update all of the elements of the subarray equal to the majority minimum, lexicographically minimum array that we can attain as a result of performing the given operations however many times we like. And they have explained what is the majority element. Basically, an element that is coming strictly more than half of the elements of the array. So like if you have an array 1 1, then 1 is the majority element here. If you have an array like 3 3 2 3, then 3 is the majority element. But if you have something like 3 2 3 2, then there is no majority element, since both 3 and 2 are having the same frequencies. Nobody is having higher frequency than the other guy. So that's it. And let's look at the sample test cases as usual. For this problem also, sample test cases will be more useful for us. Let me write this problem here also. We are being given an array of size n. We want to apply some operations on this array and make this array lexicographically smallest, like make it as small as possible lexicographically, as much as you can. And the operation that we can apply is choose a subarray which has a majority element, let's say M, that is the element having the maximum frequency. And the frequency of that element should be greater than the uh, frequency of all of the other elements, like the sum of frequencies of all of the other elements. So basically, if there is an array of size 3, then the majority element should have a frequency of at least greater than equal to 2. If the number of elements here are, let's say, 6, then the majority element should have frequency of at least greater than or equal to 4. That is, it should be greater than n by 2 if n is the number of elements in the subarray. That is how we define the majority element. So in the operation, what you will do is you will set everyone in the range from AL till AR equal to M. Like you will do this now. The problem is pretty straightforward, just this much. But doing it is like it's not too complicated, but you will have to do think about some case works. Maybe the solution might not look that difficult, but during a contest when you have no idea about what to do, and you might get some wrong intuitions, like I got an intuition regarding using a segment tree with and do some creative work with it, which later on I realized that it's not really worth it to use segment trees. So you might waste some time as well. So let's say the array is 2 1 1 2. Then the best thing that we can do here is first choose this to make it 1 1 1 2. Then choose this to make it 1, 1, 1, 1. This is the best possible thing that we can do here. Nextly, for the second test case that we have is 4 double 3 4 3 4 double 3 4 3 2 5. So when I had seen the first sample test case, the idea I had got was, if the smallest element is coming two times together, then I can just make the complete array with just the smallest value itself, right? If you are having the smallest element come twice together, then you can make all elements equal to the smallest element, um, in just the same way as we have done here. Nextly, here the smallest element is coming only once, so obviously we cannot change anyone else by using it. What we can do is, we can use the other threes or something to change the values of other people. Yep, one more thing that had come up to my mind here is, since we want to find out the lexicographically smallest possible array, it's pretty obvious that your focus is just on the first guy right now. If you manage to make it any smaller, then no matter what you put on the rest of the elements, if you're having a 3 here, this array would definitely be better than this array, right? So our goal right now is to just make this 4 any smaller. If we can make it even a little smaller, that's good for us. So the idea that I got in mind was that maybe I can try to think about the smallest guy, that is 2. Since I cannot uh, make the first guy equal to 2, like if I can find out any subarray where the guy 2 is a majority element, then I can definitely just make all the elements 2 there, and then keep on incrementing one element on the left hand side to make everybody 2 here. Like, you know, if I could just make one guy 2, like if I just had something like this, then I could make everybody equal to 2. So I will look out for 2. Since I don't have any subarray where 2 is the majority element, I will look out for the second smallest guy, that is 3. Since I can find out 3, um, a subarray where 3 is the majority element, then I can definitely make this 4 equal to 3, which got my whole array better. It got it lexicographically smaller. So this was one idea. Focus on the first guy only. By the way, during the contest, I had no idea at this point. How will I make sure that I am able to find out whether there exists any subarray where the um, guy 3 is majority element or not? And if there exists some subarrays, then how will I decide which subarray should I choose? Should I choose this subarray or this subarray or this subarray? Like I just let this thing to the like I just postpone this idea. For now, I just assume that, hey, I will figure out a way in which I will find out the majority element, you know, and I might have to find out something like either the last index till which I need to make everybody equal to that guy, or the first possible place where I'm finding it. Basically, I will think about it later on. I just thought this thing in my mind and started to think about this idea forward, that let's say if I have some way of finding the majority smallest guy who is a majority element, then what will I do? So the idea is pretty simple in this case. I would like to go from left to right, since making the leftmost element smaller is the first priority. For the first element, right now, let's say if it is something like 433, 4325, I would like to check what is the smallest element that this 4 can be replaced with. So since there is, if I can find out even a single subarray which is having 2 as a majority element, then I can definitely replace this 4 by 2. Similar thing is applied for 3. Similar thing is applied for 4, and so on. But yeah, if this guy is already 4, then I don't really want to choose any sub arrays and change anything on the right hand side to make this like all of these people 4. Instead, I will just go to the next guy and try to keep things lexicographically smaller. So all I want to do at this point is just find out if I can make it any smaller. So here somehow we will be able to somehow we will try to figure out how to make it smaller. So what we would like to do is we would like to alter as less number of elements as possible, because someday we might have a situation like 4 3 3 1 3. Let's say if the array looked like this, I wanted to replace this 4 with a 3 because that will make my array lexicographically smaller. But if I choose this whole subarray, then I will end up making this 1 into a 4 also, which is not good for me. It will make things worse. If I just I will end up making this as 3. Whereas a better thing that I could have done is just replace this to make it a 3 3 3. 3 3 3 1 3 is actually better than replacing this guy with 3 also. So the idea that we have got is I want to find out the first possible subarray where 3 is the majority element. Similarly, I want to find out for 4, for 5, for 2, for 1, for all the elements, what is the first possible subarray where that guy is the majority element. And I will just pick up for the smallest guy. Right. So in this case, this is the first possible subarray. Obviously, in some cases, you might have something like 4 1 3 3 or whatever, where you have found this one subarray which is having a majority element. So you will unfortunately have to make this one guy bigger, but this is something you can't avoid. You want to change this guy, so this guy will automatically get changed in the way. Right. So we will just avoid that case. So the whole idea that I had got so far is I just want to find out the first possible subarray where these people, where for every element, for 1, for 2, for 3, for 4, and so on, what is the first index where you are having a, um, a subarray where that guy is the majority element. Nextly, what I realized is if there exists an array where let's say X is the majority element, and let's say there are 10 elements in the array, then I can bet with you guys about one thing, that there must be at least one subarray of size 3 where you are having at least 2 occurrences of X. Right. If out of 10 or maybe even out of 11 occurrences, like in an array of size 11, if you are having the frequency of X being greater than everyone else, then it means then X must be occurring at least twice in at least one subarray of size 3. Right. So the idea that I got was, instead of looking out for subarrays, instead of looking out for longer subarrays to see if 3 is a majority element in any subarray or not, instead of looking out for all of these subarrays, I will only look out for the subarrays of sizes 2 or 3. Right. I will only look out for subarrays with size 2 or with sizes 3. If I find out these two people equal or these two people equal, then in that case, I will consider that I have found out my first majority subarray, first array with a majority element. Right. And this is something you can also try if you don't believe in me. Try to just think about any array of size 11 where X is coming 6 times or more, because it has to be the majority guy, so it must come at least 6 times. You will notice that you have to put up x in, like there will be at least one subarray of size 2 or 3 where x will come um, at least 2 times. Okay, so anyways, I believe you people are smart enough to grasp this much. So now the problem is very doable. All I want to do is, for every index, I just want to find out in this area about um, the smallest value that comes as a majority element in a summary. Yeah, it must happen something like this. And if you know, if you like just finding about the smallest value is not enough, you need to know about the place where it is coming as well. Because let's say if this is your I is equal to 2 here, and the index where this is coming is equal to, let's say, 10, then you do need to update all of these values equal to the smallest value you had here, right? Nextly, there were a few more edge cases. As far as I can recall, I found this one edge case. Like I was randomly thinking about test cases and I got this one in mind. For this one, I would not, like, the idea that I had been having earlier was I would not update this one because the smallest value that I can get is just one, and I'm already having a value one here. Now, when I get my I at this place, there is no pair, like there is no subarray in which one is the majority guy. There is no subarray of size at least two where one is the majority guy. So in that case, I will just end up repeat giving out 1 to 1, whereas the optimal answer is 1 1 1. So as a workaround, what I thought about is, like, not just for this case, but there was one more edge case that I was thinking about where you might have an I here, and it might be better to actually apply operation on a subarray where I is the last guy. Because if you are having 2 2 here and then comes 4, then actually applying an operation on this subarray will make this guy 2, which is better for us. So I just added two more conditions that, hey, if the last two people are equal and they are smaller than the current guy, then this current guy should become equal to the smaller people which were coming before it. Or in case if one last guy and one next guy are equal and they are smaller than the current guy, then also make the current guy smaller. Right? Either you can apply operation in this way or in this way, or just find out some small guy and update this whole prefix, like not prefix, but this whole subarray. And there might be a case where the current guy is already smaller than everyone else, so you don't do anything. So you will just have a little bit of case working like this one. Now things might look cluttered right now because they were cluttered even in my case. I told you about my whole thought process on how I approach the problem. And like, you start with something and you get multiple ideas. So you do think about more stuff, you know, and so on. So instead of just telling you about this path to the solution, I did focus on these things also, like the observations we made. Because of these observations that we made, the explanation is looking complicated in comparison to how it would have looked if I had only discussed this part. But I feel that for ad hoc problems, it is actually very crucial to know about these things, like all the observations that I was making, you know. And in general, in a normal discussion, I would even love to tell you about the wrong assumptions I made, but that will just unnecessarily make the problem more complicated, like even more complicated. So that is why I'm not covering that much, like covering my thought process in that much detail. And it would be even more difficult to explain for me because I had a thought process 2 hours earlier, but that is not something that easy to explain. Right. So I hope it makes sense. And please give me the feedback whether you guys like me to cover solutions in this way, where I am discussing more about the thought process. And since I am already talking about extra stuff, I can't spend that much time on every observation we that leads us to the solution. If I only talk about the solution, then I can discuss about it in more detail, like a more beginner friendly way. But you will miss out a lot of important things in that case. So just give me the feedback, whatever you feel. And let me show you the code. I think we can end this uh, live stream and after this. Okay, so the code is looking, I think, a little complicated in that editor. So for every test case, I'm first of all taking the inputs. Then I created a set of array of integers. Okay, nice. Yeah, the thing is, I wanted to find out about the smallest value and index. So I had to figure out a way also now. So what I did is I just inserted everything inside a set and I will look out for the smallest value of the set. That is the way in which I am approaching. And I populated the set completely. Um, I added this thing just because I did not want to have if else conditions for the cases like if set is empty, do this, if set is not empty, do this. So I just added something um useless. Kind of like if you have the if you have this as the first element of the set, then it won't affect the logic, but it will make my code more cleaner. It will make my code cleaner. Here I am having a few, like I'm iterating from the left to right direction from 0 to index n minus 1. And first of all, I'm clearing my set. Like this is something specific to my implementation. If you have a different implementation, you might not have this line. These are the two lines as we discussed earlier that sometimes it might be good to use the element on the left hand side for making the current element smaller. So if you can make the current element smaller by using that guy, then just make it smaller. Nextly, I'm using the set to find out the best possible value, which I can put at the current index. In case if the current value is smaller or equal to the best possible value, then just continue. Otherwise, find out the index till which I will have to update everyone. If I um, decide to make all the elements, like if I decide to make the current element equal to the best possible value I can obtain, and then I am just updating those values, and then I printed the answer. So the part related to set is something related to my implementation. Like it is very specific to my implementation. You might have a different implementation. You might consider using maps or something. That's up to you. Yep, map is actually a good way though. Okay. Anyways, so is it good enough? Like, is it clear? Shall we end the stream? Obviously, I would be there in the meeting even after the end of the recording. Okay, great. So for the ones who have been watching the video on YouTube, thanks for watching till this point. And please consider liking the video and giving your feedback in the comment section. And thank you for watching. Bye bye.